Welcome to class. In this video, we're going to take a look at some properties of the Laplace transform that make it so nice to work with in differential equations. The first property I want to talk about are S-plane translations. Essentially what I mean is I can shift my output from the transform by a factor of a if I multiply my original function by e to the at. And the proof of this is actually pretty simple, because if I look at the Laplace transform of this guy, well, by definition, that is the integral from 0 to infinity of this guy times e to the negative st. Combining like powers, I get e to the negative s minus a t f of t. And what is this guy? That is just literally f of s minus a. Right? When s minus a is my transformed variable instead of s. Right? So I can show this one. Oh, and sorry, that's the end of my proof. In just one line. Pretty simple to verify, but why is it useful? Let's look at an example. Well, now, when exponential terms show up in my Laplace transform, I can almost ignore them or just think about them as shifting my output variable s. So I know that if I just have the Laplace transform of t, that should be negative 1 over s squared. But since I have that times e to the negative 10t, I'm going to subtract negative 10 from my variable s. So the full Laplace transform of t e to the negative 10t is negative 1 over s plus 10 squared. We can also turn that idea on its head and look at what happens if I want to translate in the t-axis, or what do translations look like going through the inverse transform? Well, for some positive translation, right, a is a number greater than 0, it turns out exponentials also just turn into translations under the inverse transform. But that translation looks a little bit funkier. We do actually get the translated function, except times this ha of t, which I will be calling the Heaviside step function. You may also hear it called the characteristic function, or it could be called the unit step function. All sorts of different names for this guy, but I think a common name for it is the Heaviside step function. So ha is just 0 until it gets to a, where it becomes 1. So essentially, it kills your function before you get to a. So here I've got an example. Let's compute the inverse Laplace transform of this guy. Remember, it's a good strategy to look for the closest thing you can find on a table of transforms, which I think for this guy is going to be that the transform of sine of t is 1 over s squared plus 1. But you'll notice I've got that exponential floating around, but not to fear, right? What we get is that the Laplace transform, or excuse me, the inverse Laplace transform of e to the negative pi s, if I write it as times 1 over s squared plus 1. So because I have this e to the negative pi s, I know that that's just going to effectively translate my function backwards. I'm going to get sine of not t, but t minus pi, just like I have that e to the minus pi. But I've got to tack on this Heaviside step function at pi. Now what does this do? Well, it does nothing, actually. It just kills the function before pi. But once I get to pi, the function is just 1, so I get sine of t minus pi if t is greater than pi. And do you notice essentially what this does is it prevents us from backtracking outside of the function's domain. Here, we only specified that f of t in our definition of the Laplace transform is well defined at 0 forward. So I can't allow any values of t that are negative in my definition of the Laplace transform. By forcing any values of t that would become negative to be 0 before transforming, it keeps everything well defined. So really, the Heaviside step function is more of a theoretical attachment to say, hey, don't worry, we're good, you can do this, and it works the way you'd expect. Here's a really fun one. Turns out that by multiplying my functions by powers of t, essentially that just translates to taking derivatives of the output. If I add n factors of t, I get the nth derivative of the output I would have normally, except it alternates, which is kind of interesting. Let's see how we can use that. So here I've got the Laplace transform of t times cosine of 2t. Well, from a transform table, I know that the transform of cosine of 2t is s over s squared plus 2. So this property of Laplace transforms tells me that the transform of t cosine of 2t, notice I have t to the power 1, so I will get negative 1 to the power 1 times the first derivative, now with respect to s, of s over s squared plus 2. Jumping in with a quick typo here, sorry. 4 and 4. So that derivative is s squared minus 4 over s squared plus 4 squared. And that would be the transform. For this next property, we need a quick definition. The convolution of two piecewise continuous functions, meaning they're continuous at most finitely many points. But f and g are piecewise continuous functions defined from 0 forward. Their convolution, we use a star or an asterisk, right? F convolved with g is this integral, the integral from 0 to t of f of tau times g of t minus tau d tau. A really important point to add is that convolution does not commute necessarily. So f star g is not always the same as g star f. It is important to watch the order here. But why are we talking about them? Well, because Laplace transforms split convolution into multiplication. So if I take the transform of a convolution, I get the product of their transforms. And maybe the more powerful logical way to read this is that the inverse transform of a product is a convolution. And that can help us to find much more complicated inverse transforms like this one when I have 1 over s squared minus s, which is not one that would likely appear on most transform tables. But I can write this as 1 over s times s minus 1. So I have, or if I write it as suggestively as possible, this is 1 over s times 1 over s minus 1. And the convolution theorem tells me that I can split this inverse transform over multiplication, and I get that the inverse transform of 1 over s convolved with the inverse transform of 1 over s minus 1. And these are both transforms that I can find on a table. The inverse transform of 1 over s is just 1. And the inverse transform of 1 over s minus 1 is, well, 1 times e to the s, negative s, if I use my translation. So at the end of the day, this is just 1 convolved with e to the t. So I take the integral from 0 to t of, my first function is 1, I plug in tau, I get 1, times my second function is e to the t, I plug in t minus tau, integrate with respect to tau. That antiderivative then is negative e to the t, e to the negative tau, evaluated from tau equals 0 to t. So I get, and apologies running out of room here, I'll squish it, e to the t minus 1. It's the inverse transform.